Alrighty, let's go through the homework that you just turned in. So, number one, measurements made in 1910 indicate that the common flea is an impressive jumper. Awesome. Given its size. Assume that a flea's initial speed, right? So we immediately know initial velocity is 2.2 meters per second. 2.2 meters, it's a great M, meters per second. And that it leaps at an angle of 21 degrees. So my theta is 21 degrees with respect to the horizontal. If the jump lasts 0.16 seconds, so my delta t is 0.16 seconds. If the jump lasts 0.16 seconds, what is the magnitude of the flea's horizontal displacement, and how high does the flea jump? Right, so we have two things here. So horizontal displacement. You guys know that one of our kinematics that we love is initial velocity, and that's going to be, what's that? Delta t plus 1 half a delta t squared. You guys remember this kinematic? You love it. One of the facts that you need to remember, that if you only have horizontal displacement, or you're just considering that component and nothing else, the acceleration is 0 for the horizontal displacement, right? We're assuming nothing, like there's no air drag or anything like that, so acceleration is going to be 0. So I can actually get rid of this entire second part of the equation, because anything multiplied by 0 is in fact 0. So I'm left with this part. However, I'm only considering, that's why this is 0, I'm only considering the horizontal portion of the displacement. And so this initial velocity is the initial velocity of the overall, the resultant vector. If I only want the x component, right, the horizontal component, I am actually going to make a small change to the equation as I have it. I'm going to take the initial velocity and multiply it by the cosine of theta. So I got to have my delta t. But the cosine of theta is going to give me the adjacent side of the triangle. Right? So if I have a flea's jump like that, I look at the the vertical component and the horizontal component. This right here is the theta. Here is the horizontal component. So this is the adjacent side of the triangle. So cosine is adjacent over hypotenuse, so adjacent over hypotenuse. So taking the cosine of the initial velocity will give me the x component of that initial velocity. So let's continue that. Delta x, 2.2 meters per second. Cosine of, 21 degrees. And then 0.16 seconds. My calculator tells me that's 0.33 meters. And the question asks for magnitude, so I don't need direction. Moving on to the second part of this. Now, I'm actually going to use this same equation that I started with here, but now I'm going to pay attention to the y component, because it says, how high does the flea jump? So we know that max height is reached in a time interval of half delta t. So whatever my delta t is, half of that is going to be the time it takes, the time interval of reaching the y max. So my y max is going to be initial velocity times the sine of theta, because now we're looking at the y component, so that's now opposite the angle. So sine is opposite over hypotenuse. And then for this time interval, the time interval for y max, that's going to be delta t half plus 1 half the acceleration in the y direction. Again, half delta t, and all that gets squared. Okay? So Hug and chug. 21 degrees. And then we have 0.16 seconds divided by 2, 1/2, negative 9.81 meters per second squared. And then, am I going to run out of space? 0.16 seconds divided by 2. And then that is squared. Right now, this looks super, super scary, but I'd like to point out that all you have to do is plug this into your calculator. And if you plug this in as it looks, that y max is going to be 3.2 times 10 to the negative second meters.